All right, good evening, everybody. How's everyone doing? Everybody warm out here? All right, doing all right? Okay. So with all the excitement tonight, it's going to get hot in here, so don't worry about it. Well, welcome to the Vanderbilt Hya Observatory and to our October Meet the Astronomer lecture. So we're very happy to have you all up here. We are also live streaming to YouTube this evening, so we're going to be broadcasting to that little camera back there. But before we get started, I just have a couple of announcements and our introductions, of course. But so I'm Dr. Billy Tietz. I'm the director here at the Vanderbilt Hya Observatory, and Hya has been here. Let's see here. This will be our 72nd year on top of this hilltop. And ever since our beginning, we've done outreach to the community, whether it was schools or to our students or just the public in general. And that continues very strongly today. So, for example, this past year, we've had a little over 1,000 MNPS students up here at the observatory on field trips. So we feel very passionate about our commitment to community education. And you know, part of that is that you know, we have to fund the things that we're doing up here. So you know, if you would like to donate, we would really appreciate that, because basically everything we do up here is run, at least in part, by the generous contributions from folks like you all. So we have donate posters all around the observatory. It's a nice little QR code that you can conveniently scan, but any little thing helps. So anyway, that's my donation plug. So we've got just a couple of events left this year. It's hard to believe that we're almost into November. We have a November telescope night that is actually already sold out, but we have one scheduled for December. And we're getting tickets put online, and those should go on sale about the middle of November. And we will hopefully be continuing those in the winter months as we progress into 2026. We have one more Meet the Astronomer lecture coming up on November 20th, if I'm not mistaken. That is one of our more recent PhDs, Dr. Jessica Schoenhut-Stasek. And she'll be talking about some of the major observatories that are found out at Mauna Kea in Hawaii and some of the discoveries that they've made. So be sure to check out our website for that. Tickets go on sale tomorrow. And then if you haven't followed us on Eventbrite, our ticketing provider, make sure that you do, because whenever we add a new event, you're going to get a notification for that. And we're hopeful we're going to be adding a lot more events, especially things to do with happenings in the sky in the next few months. But so the program for tonight, it's going to go about 45, 60 minutes or so. We're then going to open up the floor to a Q&A session. Spend about 15 minutes or so doing that. And for folks that are watching on YouTube, be sure to put your questions in the chat as they come to mind. But we're going to do all the Q&A at the end. And then after the program, we will have the Seifert telescope back open again. And this time it's going to be looking at Saturn. And it ought to be a really nice view of it this evening. And then in our library back there, one of our esteemed volunteers, Mr. Lonnie Puterbaugh, has brought his extensive meteorite collection for us to be able to enjoy. And some of the pieces that are in that collection are pieces of the objects that you're going to hear about in this talk this evening. So we're especially thankful to him, and he can tell you anything and everything about those meteorites. So I dare you to try to stump him. But tonight's presenters, Dr. David Weintraub, he's a special presenter for me because he was my PhD advisor. So we've had a long relationship for a while, so it's always such a joy to be able to bring him back up here and introduce him. He is a professor of astronomy emeritus and director of the Communication of Science and Technology program emeritus at Vanderbilt University and a fellow of the American Astronomical Society. His research discoveries include identifying the first known nearby young star cluster, known as TW Hya Association, and pioneering the use of infrared speckle interferometry, infrared molecular hydrogen imaging, and submillimeter continuum imaging to identify material in the circumstellar disks of young stars. That's a mouthful, rolls right off the tongue, right? But he's also the 2015 winner of the Klopsteg Award from the American Association of Physics Teachers, which recognizes the outstanding communication and of the excitement of contemporary physics to the general public. And I think you're going to get a healthy dose of that this evening and understand why he got that award. And he's also the author of a number of books, and instead of me telling you a little bit about those, I'm now going to turn the program over to him, and he's going to talk a little bit about the books that he's written and also brought with him this evening. So join me in welcoming Dr. David Weintraub.
All right. Thank you, Billy. Can you hear me? Yes. All right, got the microphone working. I feel like a rock star with this microphone. All right. Let me first tell you about the books. I have a handful of books that are on a table inside the library. One of them is one I edited. It's a series of chapters by 38 women astronomers. It's called The Sky is for Everyone. It's about how women became involved in modern astronomy from each of their perspectives. It's, I think, a really wonderful book to read. We have 7 of them, because that's what's left in my attic at the moment, available in there. They're available for a donation to Dyer Observatory or the Dyer Observatory Endowment. So if you want to make a donation and collect a book, I'd love you to do that. The other books that are in there are 6 of them. These are books for children. They're aimed at 8 to 12-year-olds. They're called the Who Me series. Who Me, I'm a mathematician now. Who Me, I'm a radiologist now. If there's anyone here who's in that age demographic of 8 to 12, we want to give you a book. So just stop by the table, take a book. If any of the rest of you want to take 1 or more books for donations to the Dyer Endowment, we'd love for you to do that for your children, for your grandchildren. Good Christmas presents? Okay. So they're all for the Dyer Endowment if you're interested in the books. So now I'll get started. So you can see the title, The Most Intriguing Evidence That Suggests Life Beyond the Earth Might Exist. Right? I'm not going to be talking about Klingons or Spock or E.T. I had to say E.T. so my sister and brother-in-law in Washington can take their shots of makers. They said every time I say E.T., they will do that. All right. So let's move on. This is one way in which we might discover that aliens exist. Is it likely? I don't really think so, not in the near future. And at least for tonight, I'm not interested in worrying about whether intelligent aliens are out there. I'm interested in understanding the likelihood that life of any kind might exist in the universe. So what else might we pursue? Well, Mars has been an interesting place for astronomers to study for 200 years because Mars is the closest place in the universe that is Earth-like. Mars has a day that's almost exactly 24 hours like the Earth's day. It orbits the sun in about 2 years. It has a solid surface. It has polar caps. It has water. It has seasons. It has a thin atmosphere. It has clouds. It's incredibly Earth-like. And so astronomers have been pursuing possible evidence of life on Mars. One thing that we know is that Mars has a lot of water now. It's in the ice caps. It's in subsurface reservoirs. There's enough water on Mars now to create a global ocean 5 to 9 feet deep. And we know Mars has lost probably 90% of all the water it once had, which means in the past it could have had a global ocean 100 feet deep. So Mars could have looked like this in the past. Does that mean it could have had life? Maybe. The first evidence we have that was suggestive came from the Viking missions that were launched in the mid-1970s. They landed on Mars in 1976. And one of the experiments on the Viking landers was called the labeled release experiment, in which the lander grabbed some dirt from the ground, dumped it into a canister. That canister had water, it had a heater, it had radioactive carbon dioxide in it. If there were any creatures in there, they might breathe in the CO2 and exhale it somehow, and the detection of the radioactive gases might indicate there was something living there. It was an interesting experiment. And the principal investigator of that experiment thought indeed they had discovered life on Mars. He's just about the only person who ever believed that result. There's a paper that was published just 4 months ago, May 2025, suggesting, I think, the definitive answer, and that is the chemical reactions they detected were from the thermal decomposition of perchlorate. Doesn't matter what perchlorate is. It's not living stuff. So this is almost certainly not evidence of life on Mars. But there's a meteorite involved. A meteorite was found in Antarctica in 1984. It's known as ALH 84001. It was found in the Allen Hills part of Antarctica. That meteorite was shown to be a meteorite from Mars. And in 1996, some scientists looking at a slice of the inside of Mars found that little worm-like thing at the center. They said, we have found a fossil of a worm-like bacterium in this Martian meteorite. This was argued about a lot for a couple of decades. Almost certainly it's not from a living thing. It is so incredibly small that there's no way you could put living organs, even in a bacteria, inside this thing. It would be known as a nanobacteria. They don't exist. Nobody believes this is a result from Mars, a life on Mars anymore. But there's more. The Mariner 6 spacecraft, which was one of the first missions to go to Mars, it was a flyby. It didn't land on Mars. But it flew by Mars on August 5th of 1969. When it flew by, it made some measurements of the contents of the atmosphere. And in a press conference that took place 2 days after the flyby, the principal investigator of the mission said, "We are confident that we have detected gaseous methane and gaseous ammonia between approximately 61 degrees and 76 degrees south latitudes on Mars." One of his team members then said, "I have no clue as the origin of these gases." He should have just stopped there. "But I have no clue. But if the readings are true, and I believe they are, we have to face the possibility that they could be of biological origin." Why is that? All of the methane in the Earth's atmosphere is from life. It's from flatulence from goats and cows. It's from the decay that happens in rice paddies. It's from the processing of material in sewage systems. It's from oil and gas and coal excavation. 100% of it. And it has a very short lifetime in the Earth's atmosphere. If you could stop all of that production of methane from biology on the Earth today and come back in 1,000 years, there'd be no methane. The same would be true of Mars. So if you detect methane in Mars's atmosphere, it's possible that it comes from life. So maybe. There were headlines all over the world. 2 gases associated with life found on Mars near polar cap. That's the New York Times being subtle. Right? 2 days later, another NASA press conference. George Pimentel speaking again. "The spectral features previously attributed to methane and ammonia were, in fact, caused by frozen carbon dioxide, dry ice." Whoops, we shouldn't have had the first press conference. So, not evidence of life. But for the last 50 years, astronomers continue to look for evidence of methane in the atmosphere of Mars, because it would be a good clue about life. And the Mars Curiosity rover that landed on Mars in 2012 spent the first 3 years looking hard for methane and found it. In 2015, for a brief period of time, it sniffed methane. A really, really, really tiny amount of methane. A small enough amount of methane that amount of methane could be generated from meteorites and comets raining material down onto the surface of Mars, or from some reactions in the atmosphere and the soil that should not be able to produce much methane, but could produce this much. But nevertheless, it's a maybe. That maybe is still out there. And just this spring, March 2025, the rover detected alkanes, long-chain alkanes. 3.7 billion-year-old rock on Mars contained long-chain alkanes, which are organic molecules thought to be remnants of fatty acids. Well, okay. But there are other ways to make alkanes. We can't dismiss this. but I don't think chances are real good that it comes from life, but it's possible. Right? So there's a little bit hanging out there with Mars that we haven't proven definitively one way or the other yet. Let's move beyond Mars. Further out in the solar system, we have a moon of Jupiter, Europa. Europa is one of many icy moons in the outer solar system. Icy moons in that the surface is water ice. But if you have the surface of water ice, as you go down inside that moon, it gets warmer and warmer and warmer. And at some level inside, you get a global ocean of water below the surface. So inside Europa, you have a heat source that comes from the tides of Jupiter. You have water, and you have all the essential elements we think are necessary for life: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. It's possible that life could exist there. Does it? I don't know. If you put life in there, it could thrive, but that doesn't mean there's anything there. But we're going to try to find out. The Europa Clipper is a NASA mission that has also already launched to Europa. It will get there in April of 2030, so 5 years from now. It will do some measurements to try to determine in much better detail whether the subsurface oceans in Europa could support life. That's an exciting experiment coming up. Beyond Europa, if we go out to Saturn, one of the moons of Saturn is Enceladus. It's also an ice world with the icy surface and the water ocean below, and it has these incredible geysers, like giant Yellowstone geysers erupting. They erupt 100 kilometers up into space. Those eruptions will drag with them anything that's in the ocean. So if anything's living down there, if we could fly through these geysers, we might discover what's down there. And we want to do that. So NASA has come up with an idea for a mission. There's no money for it right now. It's not being built right now. It hasn't been launched yet. But it's a mission concept to go to Enceladus. It might happen in the 2050s. The European Space Agency also wants to go to Enceladus. They have their own ideas for a mission that would involve an orbiter and a lander. Enceladus is a really intriguing place, but we know nothing about what's there. Now I want to get to the meat of the talk, what I'm really interested in tonight. I want to talk about meteorites and asteroids. The Murchison meteorite, and there's a slice of that inside, the Murchison meteorite fell in Australia on September 28, 1969. It was what's called an observed fall. That means somebody saw the rock fall out of the sky. You see a fiery thing passing through the sky. You see it going that way. People chased after it and found the remnants of this meteorite. It means the remnants of the meteorite and 100 kilograms, 200 pounds of the meteorite were found. They were not sitting on the Earth for very long. So the risk of contamination from the Earth is low, but possible. This meteorite is known as a carbonaceous chondrite, which means it's very fragile. It's not a rock. It's not a hunk of iron. It's very fragile stuff. It's 4.6 billion years old. It's older than the Earth. Carbonaceous chondrites are remnants of the first stuff that formed when the Earth and Sun were forming. Inside this rock, there are little mineral grains, fragments of rocks that are older. Some of them are 7 billion years old. The grains inside this rock predate our Earth and Sun by 2.5 billion years. This is old stuff. Okay. It's also really neat stuff. Now, one of the reasons the Murchison meteorite is so interesting is because it was studied so well. And the reason it was studied so well is this happened. We went to the moon. 2 months before Murchison hit the Earth, we hit the moon. We set footprints on the moon. The significance of that is that these astronauts brought back rocks from the moon. And when those rocks came back, NASA wanted to be ready to study those rocks. And so NASA spent a whole lot of money setting up labs around the United States at different universities and at NASA centers to be able to study these rocks as carefully as possible. Now, before I tell you some of what they found, I want to become a chemist or a biologist or something that I'm not and say something about amino acids, because this is where it gets interesting. Amino acids are molecules. They have this thing called an amino group on one side that has hydrogen and nitrogen in it. It has this thing called a carboxyl group on the other side that has carbon and oxygen and hydrogen in it. And then it's got stuff in the middle. We don't really need to know tonight any more about amino acids than that, except that we know there are 500 plus different kinds of amino acids that exist in biological things on Earth. Trees, mosses, people, elephants, gather them all together, look for their amino acids. There are 500 or more of them. There are 20 of those amino acids that are essential in living things for building proteins. Proteins are long chains of amino acids, and there are 20 of them that are really, really important. The third thing we need to know about amino acids is on Earth, all the amino acids in living things are left-handed. And we'll talk about what left-handed means in a moment. But first, let's go back to Murchison. In the Murchison meteorite, 90 different amino acids were found. 19 of those are found in life on Earth, so the other 81 are not natural on Earth, hard for them to be contaminants. One of those is glycine, which is a so-called non-essential amino acid, which means your body can make it. Okay? Alanine is known as an essential amino acid, which means you have to eat it. You have to take it in. You can't make it. In addition to those amino acids, some sugars were found. Arabinose, xylose, lysose, ribose. Ribose is the most interesting one of those to me because it's found in RNA and DNA. Notably, deoxyribose was not found. What else about these? We don't think they're contaminants. Why? Because this ratio, which I'll talk about in a moment, is the ratio of right-handed to left-handed amino acids. As we said a moment ago, all the amino acids on Earth in living things are left-handed. If this is contaminants from the dirt where this meteorite hit, you should get left-handed amino acids. You shouldn't get right-handed amino acids. In addition, the sugars are enriched substantially in carbon-13, which is an isotope of carbon. Most of the carbon in carbon dioxide or anything else with carbon in it on Earth is carbon-12. In the universe, in the solar system, and other places, there are different amounts of carbon-13 versus carbon-12 than there is on Earth. The ratio of carbon-13 to carbon-12 in these things cannot come from Earth. There's too much carbon-13. The evidence that this stuff is extraterrestrial in origin is overwhelming, indisputable. Let's go back to the left and right-handed thing. This is called chirality. It's the property of something being identical if you look in the mirror. So I have two hands. Okay? I can't overlap them. They don't look the same this way. They look the same this way in the mirror. If you can get a mirror image, then these things are pretty similar, but they're not exactly the same. Now, I've got some heavy math for you down here at the bottom. If the ratio of the right-handed to left-handed amino acids is 1, then you have equal amounts of right and left-handed. If the ratio of right to left is 0, then you have no right-handed and all left-handed, 100% left-handed. That's what you are. All of your amino acids would correspond to D over L equals 0. You're left-handed for your amino acids. If all the amino acids are right-handed, or all the molecules of any sort are right-handed, then L over D is 0. So there's your math lesson for tonight. Here are some amino acids. Mirror image molecules, they've both got hydrogen, they've got this NH2 thing, they've got the COOH thing, they've got the R thing, they've got the C thing, but they're not identical. They're mirror images of each other. Try to look at them closely and figure out why they're mirror images and not exactly the same, but they're mirror images. Okay? The left-handed amino acids, that's what's in your proteins, that's what's in your body. The right-handed amino acids, they're not made in biology on Earth. They're not used by biology on Earth. Okay, in terrestrial biology, the amino acids that are used to make these proteins, chains of amino acids. They are 100% left-handed. In terrestrial biology, the amino acids that are the building blocks of RNA and DNA, the adenine, the thymine, the cytosine, the guanine, they are left-handed, 100%. Now, interestingly, in living stuff on Earth, the sugars like the ribose, the deoxyribose, that are key building blocks of RNA and DNA, right? They represent the structure of the DNA molecule. They are right-handed, not left-handed. It's one or the other. Why life on Earth is like that, I can't tell you. I don't think anyone can tell us. But at some point, life on Earth somehow chose that all the amino acids we're going to use is left-handed and all the sugars we're going to use are going to be right-handed. And the other stuff, can't use. That's life on Earth. Let's look at some more amino acids. Look at more meteorites, excuse me. The meteorite Northwest Africa 801 was another observed fall. Fell in 2001. There are about 5 kilograms or 10 pounds of that meteorite that have been found. In that meteorite, a number of sugars have been found: ribose, arabinose, xylose, and lixose. In addition, we know that, like with Murchison, these sugars are isotopically distinct in having way too much carbon-13 than carbon-12. This is, again, clear evidence that in this second meteorite, there's extraterrestrial organic stuff. Not living stuff, but important organic molecules. The Ivuna meteorite, which fell in 1938 in Tanzania, we have 705 grams of that stuff, so a little more than a pound of that meteorite. It's probably the fragment of a comet. And Orguiel, another meteorite that fell in 1864 in France, which is also probably a fragment of a comet. In these two amino acids, in these two meteorites, the amino acids alanine and glycine have been found. In addition, butyric acid is found. That's something that's found in butter and cheese in your gut. And then for all of these, the right-handed to left-handed ratio is 1, equal amounts of each. This is not terrestrial contamination. The Tarda meteorite, it was an observed fall in Morocco in 2020, fairly recently. Again, as an observed fall, it was collected quickly after it hit the ground. Just less than 9 pounds of this meteorite and fragments have been discovered. It appears to be from an asteroid from the outer solar system rather than the inner solar system. In this meteorite, chemists have found alanine, glycine, glutamic acid, and butyric acid. The alanine has an enhanced deuterium to an enhanced right-handed to left-handed ratio, but it's not 1-to-1. There are other amino acids that were found in this meteorite. They're not in biological stuff, okay? And they're also not in the sand in which the meteorite hit. So you sample the sand, which would contaminate the meteorite. You sample the meteorite, you don't find those amino acids in the sand. These meteorites are coming from space. And now the Allende meteorite, a sample of that is inside. The Allende meteorite was another observed fall, February 8, 1969, so this was 5 months before the moon landing. Because of the timing, it also was studied very intensively soon after it fell. There's a lot of this one. There are 2 tons from this meteorite, lots of fragments. Okay. In Allende, alanine, glycine, hydroxylglycine, which is found in fungi, have all been found, and these, like in the other meteorites, are isotopically distinct from terrestrial materials in their carbon-13 to carbon-12 ratio. One more for you, the Murray meteorite. This one is close to home because some astronomers at Vanderbilt helped chase down fragments of this meteorite in Murray, Kentucky in 1950. In the Murray meteorite, there are 17 amino acids that have been found, including alanine and glutamic acid. 6 of them are what are called proteinogenic, which means they're part of the building blocks of proteins in you and me. The right-handed to left-handed ratio, 1. Equal amounts of right-handed and left-handed. They're not terrestrial contaminants. Lots of these meteorites, they're all carbonaceous chondrites. They're very fragile meteorites. They're meteorites that haven't been heated or destroyed for 4.5 billion years. They're remnants of the first materials out of which the sun and planets formed, and they have amino acids and sugars in them. Let's move from meteorites to asteroids, because this is recent stuff, and this is pretty cool. All right? The asteroid Ryugu has a 1.3-year orbit around the sun, so it's close to the Earth, relatively speaking. It spins in about 7.5 hours. The Japanese space agency launched a satellite called Hayabusa 2 in December of 2014 to this asteroid. It got to the asteroid in 2019, and it grabbed a sample of the material from the surface of the asteroid and brought it home, brought it back to Earth to be studied in Earth labs. This stuff's not contaminated. It came from outer space. And this is a movie taken by the spacecraft of the asteroid rotating. Okay? It's small, 0.6 of a mile across. It's not spherical, it's kind of diamondish shape. It's neat. I mean, we went to an asteroid and took a movie of it from up close. That's just amazing. Okay. What did we find in Ryugu? Uracil, which is found in DNA. Niacin, which is vitamin B3. 7% of this asteroid, or the material we brought back, is water. 20 different amino acids have been found, including glycine, alanine, and these are equally right and left-handed. It's not terrestrial contaminants. This asteroid has amino acids in it. That's just really cool, all right? That's not the only one, though. NASA did the same thing. Asteroid Bennu is an asteroid in a 1.2-year orbit, so again, very close to the Earth as we orbit the sun. It comes closer than the moon every 6 years. It's got a 4.3-hour day. NASA launched a mission known as OSIRIS-REx in September of 2016, and it arrived at Bennu in October of 2020, took a sample, and returned to Earth, dropping down into Utah on September 24th, 2023, 2 years ago. And of course, we now have the obligatory rotating asteroid movie. Okay? It's just amazing that we can go there and do this. Okay? This is the size of Bennu. It's about the size of the Empire State Building. It's the size of a large football stadium, right? Imagine it. It's not a giant asteroid. It's a small little thing, which also means its gravity is weak, which is why we can go to it and grab a piece of it and escape its gravity and bring it home. This is a close-up. That big boulder in the middle is about 24 feet across. So it's now half the size of this room we're sitting in. Bennu is a carbon-rich asteroid, which means it's the kind of asteroid from which carbonaceous chondritic meteorites would be broken off of. Okay? It contains clays. Clays are minerals that form in water-rich environments. We think it formed in the outer solar system well beyond Jupiter. It's probably a fragment of what was once a much larger object that would have provided the heat, that would have provided the ability for this thing to make the clays. The OSIRIS-REx mission brought back 4.3 ounces of this asteroid. And I'm going to show you a movie. It's very quick. It'll go over and over and over again. But this is the spacecraft bouncing off the surface and grabbing some dust from the surface. So it's filming itself, bouncing off the surface. And in bouncing off the surface, some material from the surface bounced up into the foot, and this is what came back, right? So this is the stuff that it collected by bouncing off the surface of Asteroid Bennu. In that material, there are salt minerals. I mean, these are cool, right? On Earth, how do you get salty minerals like this? You evaporate water from a salty liquid. That doesn't mean it had to happen this way in Bennu, but it probably did. Probably once upon a time, Bennu was part of a larger asteroid that was warm and wet, and the water evaporated and left behind these salts. In this image, the phosphorus is green, the calcium's red, the iron is yellow, the magnesium is blue. There's this long cluster in the middle, which is sodium phosphate. That's also formed by evaporation. Neat stuff. Inside Bennu, lots of ammonia has been found. Ammonia is NH3. Okay? This tells us that Bennu came from the outer solar system. Asteroids in the asteroid belt between the orbits of Mars and Jupiter, you're not going to find ammonia. You find ammonia in stuff that's in the very outer solar system, where it was much colder when the planets and asteroids and other objects formed. In Bennu, you know this was coming, the amino acids in Bennu are equally right-handed and left-handed. You know they're not contaminants from Earth. Okay? This asteroid has amino acids, and they came from the asteroid. How many of them? These are the 20 amino acids that somehow or other bond together to form the proteins in all of us. 14 of these 20 amino acids were found in Bennu. 14 of them. In Bennu, there are 5 nucleotide bases that are in RNA and DNA: guanine, cytosine, adenine, thymine, uracil. All of them were found in Bennu. Amazing. So what does this mean? I can't tell you what it means. I can tell you what I think it means. Okay? We live in this place called the Milky Way. That's home. All right? There are a few 100 billion stars in the Milky Way. And somewhere out there in the Milky Way, maybe in these dark clouds in which stars form, maybe in these star-forming nebulae like Orion, amino acids and sugars were made. Maybe it happened in the disk around the sun, where all these rocks were growing and accreting together, sticking together to make the Earth and the other planets. Somewhere along that chain, the universe has figured out how to make amino acids and sugars. These are complex molecules. We're not talking about carbon dioxide, water, and ammonia. The very simplest molecules you could have that have carbon and nitrogen and oxygen and hydrogen. The stuff you need to make life. Which means 4.5 billion years ago, when the Earth formed, it collected that stuff. And for 500 million years, this stuff continued to rain down onto the surface of the Earth as the solar system cleaned itself up. And 4 billion years ago, this early bombardment of the Earth ended. And you have planets, and you have a sun. And on that planet called the Earth, it gradually cooled off, and you had rock, and you had some water on the surface. And we're fond of thinking of the water on the surface as that primordial soup. And in that primordial soup, 75 years ago, scientists said, well, what if in that primordial soup you had water and ammonia and carbon dioxide? And you had lightning strikes, and you had turbulence and other stuff mixing stuff together. Could you make amino acids on the Earth? You don't have to. That pool is full of amino acids. It's full of sugars. You don't have to start with the simplest molecules. The universe has given us that. Whether those amino acids and sugars formed into RNA and DNA and other living things in those pools, or maybe in the deep sea vents, maybe somehow attached to clay minerals below the surface, we don't know how it got started. But somehow, by the time the Earth was 3.5 billion years old, these things called stromatolites existed. They're one of my favorite things. I got to go to Australia to see some stromatolites. Okay? Stromatolites, these are big, okay? Like this table in the middle of the room. Okay? These are not individual cells. These are colonies. Think of them as being like coral reefs. They're colonies made from mats of blue-green algae. That's photosynthetic stuff. It's also known as cyanobacteria. So you get these mats of blue-green algae. They do photosynthesis, okay, which means they produce oxygen. This is how the Earth began to oxygenate the atmosphere. You need oxygen. The early Earth did not have an oxygen-rich atmosphere. The stromatolites got that going. 500 million years after the Earth had really settled down, we didn't just have individual cells somewhere around, lying around the Earth. We had colonies. And they've left behind fossil stromatolites to tell us we slept here. It didn't take the Earth very long to create primitive life. I don't know how life got started on Earth, but we're here. But what I know is it's very possible that the same stuff that seeded the Earth with those amino acids and those sugars, it's seeding every planet that exists around every other star in the Milky Way, and probably every other planet around every other star in the universe, because there shouldn't be anything special about what's going on here. If the stuff that helped form the Earth already had the amino acids and sugars in it, we got a big head start toward the evolutionary production of us. We didn't have to start from nothing. We got to start with all that stuff that the meteorites gave us. That's my story. Okay, so thank you, and I'll take questions. Yes?
Is there a temperature range that the acids can be formed and not be formed?
A temperature range for the asteroids?
Well, no, for the amino acids.
For the amino acids? Yeah. There certainly must be. I don't know the answer to that. If it's too hot, you'd destroy them. If it's too cold, not much chemistry happens. So it's somewhere in between, but I don't know what that would be.
Let me pass around the microphone.
Okay, you made mention of the right and left hand business, that it's only left hand here, but non-terrestrial is right and left-handed. So with all that populating going on 3.5, 4 billion years ago, any prevailing theories about why the left hand and the right hand disappeared and the left hand is voila, all we got?
I don't have an answer to that. There's certainly lots of people who study this, biologists who must have thought about it, but somehow I would guess the first more complex molecules that formed, this one formed from a left-handed amino acid, and it was dominant. It found a way to reproduce itself, and the right-handed ones got left behind. I mean, I think that's, in a very simplistic way, the idea. If it was, it must have been a random process in which it was equally easy to use the left-handed or the right-handed, but they didn't work together, and the left-handed won. I mean, if we went to another world and this happened in some other world, they could be right-handed.
Has there been any, all the ones that you mentioned, they are all equal ratios. Has there been any found that has, primarily right-handed? That's question number one. And question number 2 relates to what you said earlier in the talk about observed meteorite falls. And I'm gathered that the significance of that is that it's collected quickly, so less chance of it being contaminated. But are meteorite falls predictable events? Who are these folks observing these falls?
Okay. 2 questions, if I could remember them. Okay. The first one was, have any meteorites been found and studied in which all the amino acids are left-handed or all the amino acids are right-handed? And the answer is no. These are the only ones I know of in which amino acids and sugars have been found. Okay. Google might find you another one, but those are the ones I know about. And in all of them, they're nearly 1-to-1. There's no left-handed or right-handed bias in the meteorites or the 2 asteroids. The second question was about the significance of meteorite falls. Okay. It's clear that the main reason we're interested in those as opposed to a meteorite find is we know they're not contaminated. Okay. The meteorite I showed you from Mars, that was sitting on the ice in Antarctica for 2 million years. Okay. All sorts of things could have happened to it while it was sitting on the ice. Other meteorites have been sitting on the Earth for billions of years. It's hard to know what's a contaminant in one of those and what's not. In addition, these falls are all carbonaceous chondrites. If a carbonaceous chondrite fell on the Earth 5 million years ago, you'd never find it. It's too fragile. It would have been crushed somehow. It would have disappeared. An iron meteorite that fell 5 million years ago or 400 million years ago, you could identify it because iron, it's hard. It doesn't erode easily. But the falls are important because you know the amount of contamination is limited, but also because this is the only place you're going to find carbonaceous chondritic meteorites.
But are they predictable?
Are they predictable? No. Meteorite falls are predictable in a statistical sense in that I can guarantee you that sometime this year there will be a meteorite fall. I can't tell you where or when, but it happens often enough that one of them is going to happen. Now, most of those falls are not going to be carbonaceous chondritic meteorites, but falls are going to happen with some level of regularity, but again, I don't know the statistics of how often. But if you want to go out tonight and see a meteorite fall, you're going to have a long night. Okay?
Hello, thank you for your presentation. I apologize, I also do have 2 questions. First one, whenever they probe the meteorite like that and break it up, does that affect the meteorites or the asteroid's orbit at all?
For these asteroids, when we bounce off it, these are such small spacecraft that they shouldn't affect the asteroid's orbit? That's a really interesting question. There's a different NASA mission, and I don't know the name of it, but there's a different NASA mission that was executed within the last few years in which we actually tried to affect the orbit of the asteroid by smashing into it really hard.
Did they have to calculate all of the possible outcomes that it could hit something?
Well, our spacecraft, compared to the size of the asteroid, if you want to affect it, it can't be a really big asteroid. And if you think you might affect its orbit, you'd better hit it in a way that won't send it into New York City. Okay? But the level at which we can impact and affect the asteroid's orbit at this point is minuscule. Okay. I think they did that experiment, and the answer was, yeah, we affected its orbit just a smidgen, which says that in the future we should be able to develop more techniques to do this. And I think over the next century, I don't think I'll live to see it, but some of the youngsters here might, I think we'll be moving asteroids around. I think we'll be harvesting asteroids. We're going to learn how to change their orbits and haul them into Earth orbit or haul them to the backside of the moon and build factories on the moon, and we're going to work with asteroids. That's in the near future. And this is the first step toward that.
Cool. Okay, and then second question, if I were to see a falling meteorite, what is the best way to preserve it in that moment?
If you saw a meteorite fall, ideally you'd collect it as soon as it got to the ground. You know, use a latex glove or something so you don't contaminate it with the oils from your hand, and put it in a baggie. And then take it to Johnson Space Center in Houston and say, look what I've got. Yes.
I have two questions.
Bill, let's get the microphone for you.
So, with the Mars, those leopard spots that were discovered, what do you think those were? Have you seen those?
Okay, there was a stone discovered on Mars with so-called leopard spots. It's got little spots on the rock, which I guess the geologist involved in the project thought this is the kind of spot that maybe can be formed by biology. I don't know much about that leopard spot. I have my doubts about it for Mars. I think Mars is hospitable to life. I think Mars was very hospitable to life a long time ago. I think the evidence that has been found isn't going to prove anything. But that doesn't mean there was never life on Mars.
And do you think the 3-1 Atlas asteroid is a spacecraft?
Do I think the 3-1 Atlas asteroid is a spacecraft? No. For those of you who don't know about that asteroid, there are 3 objects that have been found over the last 10 years, which are clearly interstellar objects. They're comets and asteroids, for the most part, are things that orbit the sun, and through collisions or gravitational interactions, they get thrown into new orbits, and the comets come close to the sun and we see them. The asteroids come close to the sun and we see them as near-Earth asteroids. These 3 objects are none of those. They're on trajectories that have them coming in past the Earth, past the sun, and they're moving in such a way that they're going to keep on going and they're going to leave. Okay. They have what's known as escape velocity from the sun. You can't have that unless you started beyond the sun. So they're interstellar asteroids or interstellar comets. They're objects that did not come from our solar system. They're incredible discoveries. They're not spacecraft. They're rocks. At least 2 of them have kind of elongated cigar-like shapes. We know that from using radio telescopes to bounce signals off of them to measure their shapes. That's weird, but that doesn't make them spacecraft. Okay? There are, I'd say, a few folks who are pretty good at getting their names in the news, who can say outrageous things like, that must be an interstellar spacecraft. There's no evidence for it. It's not.
The mic.
We have microphone problems in back. We're working on it.
Yes, thank you. We're really enjoying this, and I'm a novice, but I had several geologists in my family. And I'm wondering on we've got 20 acres in Mount Juliet, and I'm digging up coral all the time from the inland flood that came through here. Are there stromolites?
Stromatolites?
Is that the same type?
Unlikely. Stromatolites grow in anaerobic environments. They grow in environments that are very salty, twice as salty at least as normal seawater, and are very oxygen poor. If you put them in oxygen-rich environments for extended periods of time, you'll kill them. So these stromatolites have to get covered by the tides for significant portions of every day. Okay? There are just a few places on the planet where they can thrive still.
Thank you.
I have a question, obviously. I'm curious, so like a lot of your presentation tonight, which has been delicious, thank you. It seems like the research questions that you presented are like what amino acids are found. What other questions are people asking about asteroids and meteorites as they fall? And like what are some of the other answers outside of just what amino acids live on them?
Okay, so what else might be interesting about asteroids and meteorites?
Yeah.
Clearly, there's a biological question which I was addressing tonight. I think the main other question would be mineralogical. Okay? I think if you find an iron-rich asteroid, it's likely to have a lot of minerals, elements in it, that we would like to have a lot of, the rare earth elements that we need for computers, modern technology. If you could identify an asteroid that had the good stuff in it that you need for manufacturing things, and you could haul it to a near-Earth manufacturing and mining facility, you'd be quite wealthy, right? So I think one of the goals for astronomers and chemists right now is to figure out how to identify the asteroids that will be most valuable for future industrial uses by us. I would say the third thing that interests us with asteroids in particular is making sure they don't wipe us out. Okay? So a big project in astronomy right now is identifying so-called near-Earth asteroids, asteroids that come near enough to the Earth that over the next few thousand years, the gravitational interactions between the asteroids and Mars and the Earth and the Moon and Venus, which will slightly change their orbits over time, will any of them end up in orbits that could collide with the Earth? And every year you read about another asteroid that's been found for which it looks like it might have a 1% chance of colliding with the Earth in June of 2076. That asteroid is then going to be studied intensively by other astronomers to map out its orbit more carefully. And after we have more data about the orbit of that asteroid, you'll see another news release. It will be on page 17, not on page 1, which says, no, it's not going to hit the Earth. But it may come close, but don't worry about it. But it's a serious concern, because if an asteroid hit the Earth, the main reason to worry about an asteroid hitting the Earth isn't that, if it hit Nashville, we wouldn't be here to talk about it. But it won't destroy the Earth. But an asteroid collision with the Earth, if we don't know it's coming, the seismometers that measure the earthquakes waves that come out from that are identical with what you'd expect from a nuclear bomb detonated on Nashville. And then somebody else might decide that somebody launched a nuclear missile and blew up Nashville, and we'd better launch our nuclear missiles at them and blow them up, and then we might destroy the Earth because we didn't know it was an asteroid. That's the concern. So I'd say there are three things going on. One is industrial, mineralogical, one is biological, and one is safety.
That would be number one on my list.
You talked a lot about where these meteorites come from. So part A, how do you know where they come from? For example, how do you know the one that they found in the Antarctic was from Mars? And how do you assess really how old they are? You said the inside of one of those was 7 billion. I mean, how do they kind of tell that?
Okay, two different questions. The first one was about how we know the Martian meteorite is from Mars. The reason we know that is because we have been to Mars, the Viking landers initially and other spacecraft now. We have measured the gases in Mars's atmosphere. And the gases in Mars's atmosphere, let's say the carbon dioxide, has a particular ratio of carbon-13 to carbon-12 in the CO2 molecules. The other gases in the atmosphere have particular ratios of one argon isotope to another argon isotope. Mars has its own isotopic signature of the gases. The Earth has its own isotopic signature. Venus has its own isotopic signature. Those are like fingerprinting the atmospheres. And in the Martian meteorites, there are embedded gas bubbles which we can extract and measure the gases in those bubbles, and those gas bubbles say, I'm from Mars. Okay? So that's how the meteorites have been identified as from Mars. The second question I've forgotten. How do we assess how old they are? That comes from radioactive decay. You find certain materials inside the meteorites, like uranium, which has multiple isotopes of uranium or lead, and you measure the isotopic ratios of those species, and from those ratios you can determine when it formed and how long it's been decaying. Right? So that's how radioactive dating works on rocks on Earth. It works the same way with the meteoritic samples.
Let's do one more question over here, and Dr. Weintraub will be around for a little while for extras.
So in the amino acids that you find, I guess the link to life, I'm kind of wondering how many amino acids do you need to get a singular cellular organism?
How many amino acids do you need to get a single cellular organism? I'm not a biologist. I know that you need 20 of them for me. Okay?
For one individual cell, how many amino acids are in that?
And for one individual cell, how many amino acids are in that? I'm not a biologist, I don't know. I would imagine that you could extract a particular cell from my body that doesn't have all 20 of them in it, because it has this set of proteins and not that set of proteins, but I don't know that answer. I do know that we have not yet found all 20 amino acids that are in human-related proteins in meteorites. So maybe some of those amino acids had to be manufactured from the get-go on Earth, maybe, or maybe we just haven't found them yet. Okay. So thank you very much.
Oh,
I'll be around.
hold on one second. We don't want to forget our folks on YouTube. We had one person ask, have any di or polypeptides been observed?
Have any di or polypeptides
like
been
dipeptide or polypeptide, I guess.
I have no idea what a dipeptide or polypeptide is.
Okay, but have they been observed?
Have they been observed?
I don't know what they are
Okay.
either, so.
I haven't found any evidence of those words being used by chemists
Okay.
to describe what they've found.
That's a very satisfactory answer. All right. Well, thank you so much, Dr. Weintraub. Let's give him a huge round of applause. And thanks to everybody else for being here this evening, and for folks on YouTube watching from home. If you have additional questions, Dr. Weintraub will be around for a little while, and I'm sure he'd love to take those. But we also have the Seyfert telescope open, and it is looking at Saturn now. And if you recall back at the beginning of the talk, Dr. Weintraub mentioned the books that are here. So for our youngsters, they get a free copy of a book. But if anybody else would like any copies, we've got QR codes for a donation. So once you do a little donation, just grab you the copy of the book that you would like. Again, thank you all so much for being here.